unfortunately, when I recorded episode 4, I had a little bit of a Linux audio case, which was fun. So there was no audio, so I'm just going to redo the episode, but it'll probably go a lot faster now that it's fresh in my head. I'll try to slow down and remember the parts that were hard, but just know that I'm probably going a bit fast. One more thing, also know that you should definitely be following along if you can. Following along interactively, messing around with, hashtag checks and hashtag evals is really important, and trying to prove some of these on your own is very important to learning. So I already did these without audio. These are proofs in tactic mode. I'm going to leave them up, and we'll just do, just for the sake of doing it slightly differently, we'll do these in term mode. I'm just going to go ahead and copy this. Sorry. And we'll copy this one too. So in the first case, we had to prove that implication distributes over the argument, over an or, and converts it to an and. This is similar to saying P or Q and R, and getting P and R or Q and R. Okay, so how are we going to do this? Well, we need to use, in tactic mode, it was somewhat more straightforward. We declared our two halves, our modus ponens reversed, and we did that. That let us do intros, and then we could define our left and right for either side of the ands. But in term mode, we need to use a lot more functions and lambdas because we don't have access to have. That being said, we do have access to let. So let is kind of the equivalent. So I'm just going to copy this here and this here, and we'll change these to lets. We have let MP and let MPR. And of course, we have to get rid of the by. Sorry. All right, and then we can give back just the exact if.intro MP MPR. Okay. So in the first case, of course, it's a function. So to prove a function, prove an implication, we have to give a function. Lambda P or Q to R. And so this is actually going to take a function, P or Q to R. So we'll just call it hpqr for short. And that function is going to give back an and. So we know we need an and here. I'm just going to start the brackets right away. And in the first case, we're going to need to give back a function. And in the second case, we're going to need to give back a function. I'm just going to go ahead and fill those in with placeholders. The first case is going to take HP, sorry, and the second case is going to take an HQ, sorry. And now we're getting an error message because I forgot the commas. The angle bracket constructor takes the syntax as a sequence of expressions separated by commas. And now we need to just figure out what we're going to do for each case. So in HP, in this case, we have the left side of the and with P. We need to show R. And we already have a function. I mean, once we put in all these lambdas and got our arguments named, it becomes much clearer how to solve these kinds of problems, right? Now it's somewhat clear that we need a P or Q, and that we have a P, and that we need to show R. And so clearly, if we see our goal at the end of some hypothesis in an implication, that means that we just need to be able to give the requirements to that hypothesis to get the goal. So to get P or Q from P, we're going to have to just use or injection just to get the or q on the right side of the or. So that will look like this, or.inr hp. And now we're going to have to not forget to apply that, apply hpqr to that to get the right result. And we get an application type mismatch. Argument hp has type p, but it's expected to have type q. And that just means that we're using the wrong side. We're going to take left injection. And that's just because they decided to name left injection instead of the thing you're injecting, the thing that you're keeping. So injection left is to add something to the right. That naming convention very much confuses me, but okay. Clearly, we're going to have some symmetry here. We'll need the opposite side in the opposite case, right? Okay, and now for the second case, we have to show that a function that takes two functions, p to r and q to r, can return another function. So it's just functions everywhere. So we're going to do pattern matching directly in the arguments. We're going to say this is hpq, hpr, and then we're going to say the second one is hqr. And what are we going to return? We're going to return another function, lambda. Oops. And this other function is going to take a p or a q. And now we just have to return an r, right? Okay, so how do we return? Wait, no, I noticed now that I messed up somewhere. If this is, oh, no, okay, I thought for a second there that the goal was p or q to r, which would have meant that I hadn't introduced enough hypotheses. But now the goal doesn't have any more implications, which means I've introduced all the lambdas I can. And now we have to actually show that from p or q and a function p to r and a function q to r, we can show r. And this is just case split on hpq, right? Now, because I have so conveniently these two functions to r, these hypotheses match or.elim exactly. So instead of doing match, so down here, what we did was we matched p or q with either case, and then we applied the function in either case, the corresponding function, hpr or hqr, to either side of the or. Instead of doing that, we're just going to notice that we have exactly what we need for or.elim. And or.elim is going to take an or. We have our hpq, which is our or, and then either side, a function from either side of the or to r. So hpr and hqr for either side of the or. Okay, great. So in the second example, we're going to look at our first proof involving not. We need to show that basically not distributes over p or q to get p and q. So how we're going to do that is we're going to show two functions from either one, just like we've been doing. We're going to have let mp, and let mp is going to be this type, except to the right. And then we're going to have let mpr, which will be the reverse, from not p and q to not p or q. And of course, at the end, we have to return an if and only if of both of those two cases. to be with exact because we're doing this in tactic mode. Sorry, it's should not be in tactic mode here. We're using term mode again. I already did it in tactic mode. And in tactic mode, it looks like this. We just have the two cases, have MP, have hpqr. In the first case, we built up either side of the left and rights. And in the second case, we did pattern matching on the or. So let's see how we'll do it in term mode without the Or.intro tactics and stuff like that. What we're going to do is immediately we know we need a lambda. But we're also going to recognize, just for demonstration purposes, that we're going to recognize that the first argument is itself a function. And that's not going to let us do much yet, but it's good to know. Remember that a function not is a function from its argument to false. So we have h not p or q, and now we need to show not p and not q. And this is where if you're a beginner in Lean, you might get stuck, because how do we get, if I put a sorry here, how do we get two things in our goal from nothing? Like, how do we build these not p's and not q's if we don't even have a p or q to begin with? And it's just, again, very important to understand that usually the answer to building something in Lean or deconstructing it is a function. So, or more specifically, a lambda function, right? Function expression. So we can always build something of not p by simply constructing a lambda. That's going to look like this. I'll put in the angle brackets for the and. By simply constructing a lambda from p to false. So we have to be able to prove false here, but we can always construct the lambda from p. And of course, we can do the same with not q. Okay, so why is Lean complaining here? Insufficient number of arguments. Forgot the commas again. Great. So now we have to show false. And now we have something. We have p. Great. But how do we get false from what we have? Well, hpqr says that if you can give me a p or a q, I can give you back false, right? It is also a function. So I'll just apply hpqr to an or, and we know how to make an or from one side. That's with injection. So this is going to be, let's see if I guess it correctly this time. I'm going to guess right. Nope, I never get it right. Okay. Oh no, they were both wrong. Whoops, I didn't change the right thing. Okay. Injection left. And of course, same strategy down here. Injection on the right of Q. Okay. And that should be clear to you if you understand the nots as functions. If you don't understand why this works, I recommend that you go through this proof on your own, and everywhere you see a not, replace it with that function. So for example, q to false. And this will let you see things a bit more precisely about what's going on in the background. Okay. And in the other case, we need to show that given not p and not q, that implies not p or q. So in this case, of course, we need a function, and it's going to take as an argument an and. So we're going to do pattern matching directly on that and. We have h not p, which is itself a function, and h not q. And we need to give back another function, because it's a not, p or q. And so we'll do that in a new line, lambda, p or q. And now we have to do something with an or. Well, we know from our cheat sheet that an or can be pattern matched on with either cases in tactic mode or match in term mode. We're in term mode, so we're going to do match. And we're going to match it with or.injection on the right for the first constructor. And that will be, I believe, an HP. I could be wrong here. I'm silently guessing. An HQ, right? Q. I'm going to keep the order here, but start from the left and the right, which makes more sense. Okay, so now we have to show false over here. And how do we show false from this? Well, this is clearly, as of this point in the goal, I mean, this is clearly a contradiction. We have not P and we have P. And so there's a function called absurd that would work for this. In the general case, we could give observe H not P and HP. Whoops, it wants the first one first. And that would work. But we don't need absurd. Absurd is, I believe, a more general case of just the specific proof by contradiction defined by not being a function from something to false, which means that we can just apply HNP directly to HP because it's a function, and to get false. Okay, and that means we can do this down here too, H naught Q, HQ, and we're done.